Okay. Okay, let's get started today's class. Okay. So, in the previous class, we learned about some basic concept of instruction, right? So, uh, so you can understand the this figure, okay? So you can understand that processor, the meaning of the role of processor. Okay, so input is given to a processor, and then processor execute the promised. The promised. So promised means that the output of instructions is defined in instruction set architecture, okay, like the ARM architecture or x86 architecture. And then so processor generate the defined outputs, okay, and then what are defined outputs? I mentioned that architectural states are changing, and then architectural states are register files and main memory. Okay, so you can understand that instructions change the data in register files or main memory. Okay, so those are architectural states in computer system. Okay, and then so we briefly learned about the RISC-V instruction set architecture. Okay, so you can the RISC-V is the RISC type, so reduced instruction set computer. Okay, so it means that this type of instructions are simpler. Okay, simpler than CISC type instructions. Okay, like the x86 instructions. So that's I briefly explained about the compilation process. Okay, so compilation means that the high-level language codes are translated into machine code. So it is because the computer systems can only understand digital signals, right? So we need to translate our high-level language code into digital signals, okay? And then these digital signal codes are called machine code, okay? And the machine codes are also defined in instruction set architecture. Also, so we learned that instructions. So these translated instructions are also stored in memory, right? And actually, in order to access the data in memory, we require addresses, okay? And then the addresses of instructions are PC. This PC is called PC, okay? So it's very important. So you need to understand the concept of PC, okay? So PC is an address for instructions, okay? So by accessing instructions in memory, and the instructions are given to a processor, and then processor execute the fetched instructions. Okay. So this is the example, and then what is stored? Instructions are stored, as I explained. Also, data is stored, obviously, right? So, and then you need to understand the address, okay? So what is an address of a memory? So it's similar to the unit number in condominium. It is called a condominium in US, in the US, but it's called apartment in Korea. So you can understand the address is the kind of a unit number of condominium or apartment. Okay, so if we know the unit number of apartment, then we can access, so we can find some target unit, right? So it's the same. Though actually, in our computer systems, we store data in memory, and then in order to specify the location of data in memory, then we use address, right? So, and then computer system, actually the address number one assigns the 1 byte of data. Okay. So it means that this is the address number 0, and then this is the address number 1, and then address number 0 assigns the 1 byte of data. Then what is a byte? Byte is a 8-bit, right? And then the next address number 1 also assigns the another 1 byte of data. Okay. Then using the size of the address field, then we can also figure out the maximum size of data that can be stored in the memory. What does that mean? So let us assume that the address bit size is the 32-bit for the address field. Okay, 32-bit. Then what is the maximum size that can be accessed by this 32-bit address field? So using the 32-bit address, we can identify 2 to the power of 32 different addresses, right? Then what is the size of data that can be accessed by this address field? What is the maximum size? It's 2 to the power of 32 multiplied by 1 byte, right? Do you understand? So I mentioned that address number 1 just assigns the 1 byte of data. So, and then there are 2 to the power of 32 different addresses. They can be represented using 32-bit address field. Okay. So the maximum size of memory is the 2 to the power of 32 multiplied by 1 byte. So it's 2 to the power 32 byte. Okay, so what is this byte? It's 4 gigabyte. Okay, because 2 to the power of 30 is the giga. Okay, so using this 32-bit address field, this computer system can have the maximum 4 gigabyte of memory. So you can calculate the maximum size of the memory like this. Okay, so and then this is very important. So you need to understand the concept of addressing in a computer system. Okay, because every data is stored in the main memory, and then as I mentioned, so in order to access the data in the main memory, and we need to use addresses. Okay, the addresses identify the location of data in memory. Okay, so then let's see some memory map of an application. So when a high-level language code is translated into machine code, and then this translated machine code is called the binary file. Okay, binary file. And in the computer system, actually, if you click the binary file, or if you just execute this binary file, then the computer system executes the binary file. Okay, so this is just a file, and then we already know that files are stored in the storage devices like SSD or hard disk drives. Okay, and if we just execute binary file, so these are compiled or translated code, right? And then binary files includes the machine instructions. And if we just execute this binary file, then binary file is transferred to the main memory. Okay, so it means that the contents, the data in this binary file is stored in the main memory, and we can access the instructions. We can access instructions or data in main memory using the address. Okay, so memory map means the range of address assigned to a certain data or certain instructions of this translated binary file. Okay, so this the memory map just shows the range of address. Okay, the range of address assigned to a certain instruction or a certain data in the binary file. Okay, so this is the address map. Okay, so the binary file includes instructions and also it includes the data. Okay, so if we write a code and then we also define a variable, so we define the data stored in variables, right? So these are data, and then these data also stored in the memory. Okay. Also, sometimes we dynamically allocate data in memory. Okay, so in C or C++, we can use malloc command or malloc function, right? That means the memory allocation function. So we can dynamically allocate data in the memory. Okay, so these are dynamic data. Okay, so in C++, we can use some different commands, right? So this is the memory map, and then also you can find that a certain address range, the data or instructions are stored. Okay, so this is just the example. So in the main binary file is launched or binary file is executed in a computer system, then operating system assigns a memory map to this binary file, and then operating system specify the certain range of address to the certain data or instruction. Okay, so this is the exception handlers, and so just you can just see that this figure. So and then text means the actually instructions. Okay, and then global data. So in the program we can also define some global data or constant numbers, and then these data also stored in the global data range address field. So address range, and then we can just access the location of global data using GP. It's a global pointer, and then also in the memory, as I mentioned, dynamically allocated data is also stored and managed in the memory. Okay, so this dynamic data is managed in the stack. Okay, so we will learn about the stack later. Okay, and then the stack memory is managed by stack pointer. Also, you can find the operating system or some I/O part in this address map. So you can just understand. So when a translated program, so the binary file is launched or executed, this address map is assigned to a binary file, and then the data is stored a certain range of address. Okay, the memory space, and then the data is stored allocated in a certain space in the memory. Okay. Okay, let's see the example. So this is the example code. It's a C code. Okay, so you can find the global variables here like int f, g, y, and then what is this? This function. This is a function, right? And then also you can find the main function here. So when a C code, translated C code, okay, the compiled C code is executed. The firstly, main function is executed. So it means that the firstly main function is called. Okay, so it's called. Okay. And then also inside of this main function, you can find the variables or data and then function called here. So this is just an example. And if this high level language code is translated into assembly code, so let's see the assembly code here. So what can you see? So this is the translated assembly code. You can find the address and machine code and then assembly code. So actually, in a binary file just includes the machine code. Okay, machine code. This is because as I mentioned, a CPU can only understand the digital data, the digital signals, and then the machine code is the digital data. So the binary file just contains is machine code. Okay, so you can see that this is the hexadecimal code. So it is because actually the code, the instruction size is 32-bit and it is too long. Okay, so that's why we use the hexadecimal number to represent the very long the binary number, right? So this is, so even though this is the hexadecimal number, so actually the computer system is the binary number, is a binary data. Okay. So anyway, so so these are compiled. Okay, compiled the machine instructions. Okay. So you can find the address here. So what is this address? So actually, this machine code. So if you see that this machine code, this is the assembly code. So equivalent assembly code. Okay. So actually, this is the one instruction. So you can find the several instructions here. Okay. Then what is this address? So this is the address. The address of an instruction. Then what is this? This is a PC, program counter. The program counter of instruction, the address of instruction. So it means in a memory of a computer system, this data is stored in the where the address is this one. So for example, the data zero, so this I call this is data, but actually this is an instruction, right? So data 00112623, so the instruction is stored in the memory, and then where the address is 10148. Okay, so it means in order to read instructions from memory, then a processor used this address. Okay, so based on this model, so the processor needs to read. So actually, the instructions needs to be provided to the processor, right? So it means actually the processor reads instructions in memory using its address. Okay, you can understand this. Okay, you can understand how instructions are read from the memory, and then so how instructions are identified. So it's addressed. Okay. So this is the example of actually function. Okay. So you can find the function here, right? So this function part is translated into machine code, like assembly code, and then this is the equivalent machine code. Okay. How about the main function? So you can find the main function here, and then also you can find the translated machine code, and then the address of this instruction. So actually you can find the JAL instruction. This is the function code. So if you see the this code, you can find that the main function holds func function, right? So this is the translated assembly code. Okay. Then let's see the memory map. So I mentioned that a binary code, a binary file is executed and these data. So instructions and data are allocated to the main memory based on this memory map. Okay, so you can find the example here. So the first part is the exception handler, right? And then above this exception handler, then you can find the text part. And then actually text part includes the instructions. Okay, so text part. Because actually, if you write a code, then this code is just a text file. Then even though the text file is translated, it's also still text file, right? So instructions are actually the text, right? So anyway, instructions are stored in this range of memory space. Okay. So, and then also you can find the global data, and then the stack memory, and then the kernel part here. Okay. Okay, let's see this instruction part. So this is the address of the memory, right? And then so I mentioned that the address of an instruction is program counter. Okay. So and then you can find that so in this code, so it's the first instruction of the main function. Okay, and then this is the translate machine code, and then what is the address of the first instruction of main function? The address of the first instruction of this main function is 10180. Okay, and then I mentioned when a binary file is executed, then we first the operating system first calls main function, right? What does that mean? Call means that the function call means that actually CPU set the program count as this address of this instruction, the first instruction in the main function, and CPU reads this machine code, okay, machine instruction from the memory. So you can find that in the memory map. So this is the address. So you can this is the okay. The address of the main memory is 10180, right? And then this is the instruction in the memory. So CPU set PC, the program counter, as the 10180, right? CPU first sets the program counter as 10180. So this is the address of the first instruction in the main function. Then CPU reads this instruction from the main memory, right? So read this instruction from the main memory because the current PC is the 10180. Okay. Then CPU execute this instruction. Okay, that's how sorry. That's how instructions are executed in CPU. Then how about the next instruction? So if you see the code, what is the next instruction? The next instruction is store word is SW, and then the machine code for the next instruction is the 001126 machine code. Okay, the machine code of the this next instruction is this one. Then how can CPU execute the next instruction? It's simple, right? So in the same way, so the address of the next instruction is 10184. Okay. Why? So this is the size of this data is 32 bit. Okay, and then this is the 4 byte. Okay. So I mentioned that the address number 1 assigns the 1 byte of data. So next, the address of the next instruction is 10184. Okay. Then how can CPU execute the next instruction? Simply, the CPU changes the PC value, the program counter value, as the PC equal 10184. So change it, then it accesses the next instruction in the main memory. Okay. Then this data is given to a CPU, and CPU can execute the this instruction, right? So in the CPU, the program counter contains the address of instructions, and then by changing its program counter values, then CPU can fetch. CPU can read the instructions in memory. Okay, so that's how instructions are executed. Instructions are read by CPU and executed by CPU. Okay, so try to understand this stored program model. Okay, this is called a stored program model in a CPU, and then this is the actually the feature of a modern computer system. Okay. Okay, so this is the memory map of the instructions, and then let's see how the high-level language code is translated into the machine code. So as I mentioned, the translation is performed by a compiler. Okay, so in Linux, we can use the GCC for the C compiler. So if we use a compiler, and we can translate the high-level language code into machine code. It means binary file. Okay. And then actually the compiler performs these steps. Okay. So this is the C program. And then if we just compile the C program, and the assembly code is generated, and the assembly code is compiled by assembler, then object file. So actually this object file includes the machine code instructions. So so actually in lab number 2, we will practice the compiler. Okay, we practice how the compilers translate the high-level language code. Okay, so anyway, so we will use the C compiler, like a GCC. C compiler on Linux. Okay. So actually, if if we just compile our binary file, high-level language code, then that O file is generated actually. Okay, so that so our high-level language code has the extension of .c, right? So .c like the hello .c, and then when the compiler compiles the hello.c, then actually object file is generated. Object file has the extension of .o, like hello.o. So if we if we do not use any options, then actually the compiler generates the final binary file. But actually, if we just set an option, then compiler generates the object file with .o, and then this object file actually includes the machine instructions. And then if we just use the -S option, then we can generate the assembly code. Okay, assembly actually has the extension of .asm or .s. Okay. So anyway, the compiler, for each file, the compiler generates the object file. And but actually the modern program includes many files or many libraries. So we can use some other libraries. So actually, very simple, very simple hello world code, like the hello world, just print out the hello world on a display. But in the hello world includes this code includes the printf function, right? So we can find the printf function in C. This is the very simple basic function that display text data or result to the display on the display. But actually, in order to use printf function, then we need to include the standard IO library in C. So it is because this print function is defined in standard IO libraries of C. You can find that. So actually in the hello world program code, you can find the include standard IO. Standard library was. So I just remember the exact name. So it means actually when a final binary file is generated, then actually this final file needs to include the object file from other libraries, like the standard IO libraries. Okay. So actually there can be multiple, or there can be many object files, and then the final binary file is generated by merging multiple object files. So like hello.c. So hello.c includes the standard IO library, and then actually this library is provided by Linux operating system. Okay, so the hello.c, so it's a very simple code. Actually, the size of this simple code is very small. Okay, so if we just compile, we just generate the object file of hello.c, then this object file just includes this text part. Okay, but the printf part is not included because we do not define the printf function in the hello.c code. So this printf function is defined and then including the standard IO library. So actually, in order to use this other functions in the library, then we need to merge these other object files. So this process is called linking. Okay, so you can find the linking here. So linking means that linking process, during the linking process, linker, okay, you can find the linker here. Linker merges multiple object files. Okay. You can find multiple object files. And then it generates the binary file. Okay. The final output of compiler is the binary file. Okay. And then if we just execute this binary file, then operating system load, operating system transfer this binary file to the memory. So this is the compilation process. Okay. So if we just compile our high-level language code, and then the binary file is generated based on these processes, and then the binary file is loaded to the memory, then we can execute our binary file. Okay. So that's why you need to learn about the compiler or operating system to understand the computer systems. Okay. So actually, the object file includes some many other data. So as I mentioned, the object file includes the instructions, but object file also includes some text segment. So this is the instruction, and then state data, and then some relocation info in a single table. Okay, so actually, in order to execute the instructions, so these data are required. So required data are also included in the object file. And then, so as I mentioned, a linker merges multiple object files, right? So, for example, if the hello world is compiled, then the standard IO needs to be merged, not to use the printf function. So this printf function part needs to be merged. Okay, so the linker just merging these multiple object files. Okay, and then the part of these object files are including the binary file. So this is called the state linking. So this is it. And then sometimes the object file, the libraries can be dynamically called or dynamically linked in the binary file. So this is called the dynamic linking. And then this is how the programs are loaded by operating system. Okay, so these are some steps. Okay, so you can just read this one. So actually, these processes are done by operating system. Okay, because operating system manages the launch of binary file. Okay, so you can actually. If you read the header, the virtual address space, and then the text, copy text and data to the memory. So this is the loading, and then set of arguments on state, and then initial registers, and then blah 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 blah. So can you understand these processes? I believe it's difficult because so we do not learn about the virtual address or some argument or some as a registers not yet. So just to read these processes, and then after so and then after we learned about some entire scope of the computer architecture discourse, then please read these sentences. Okay, so we need to learn about the virtual memory, then some arguments and registers later. Okay, so just to read the process. Okay, then just understand how binary files are executed in a computer system. Okay. So I know that this is not easy to understand because you need to learn about the virtual memory and the operating system and then some of these part. Okay. So just to be done these processes. Okay, so I believe one student posted a question that if ISA is the same, the instruction if we use the same ISA and the program is the same and the CPI is the same. I believe one student asked the question. This is a very good question, right? The answer is no. Why? So it is because compiler can apply different optimization techniques to generate a binary file. So even though a high-level language code is the same, and we can apply different types of optimizations during the compilation process. So different optimizations are applied, then different binary file will be generated. So because the instructions are different, then CPI is also different. Okay. So the answer is no. So, but if the compilation option is the same, the answer is yes. Okay. Okay. Let's see the effect of compiler optimizations. So this is the example of a certain application, and then this application is compiled with GCC, the GNU-C compiler. And then we can use the different compilation options, such as the -O1, -O2, -O3, or -O0. So actually this -O, is a capital O, defines the degree of optimizations. So it means if we just use -O3 option, it means that this optimization level is higher than the -O1 option. Okay. So let's see the effect of compiler optimizations. So you can find the relative performance. Okay. So it's the baseline is 1, and this is the no optimization. And then if we use the -O1 option in the GCC with the compiler, you can find that performance is improved. So what does that mean? The performance of a computer system, that means the performance of a software is also highly influenced by compilers. Okay? That's why compiler optimization is important. Okay. So if we use some optimization options, then we can find that the performance is improved. And then why? So what is the execution time? So T is the instruction count multiplied by CPI and multiplied TC. But this is the execution time, right? This is the clock period. But in this so we use the same hardware, so TC is the same, right? So it just to check test the impact of compilers, right? So hardware is the same. So PC is the same. So we can check the instruction count and CPI. Okay, how about the instruction count? If we use some optimization options, then we can find that instruction count is reduced. That's why performance is increased, right? So how about the CPI? So the CPI is actually increased. So what does that mean? With some high degree optimization options, compiler reduce the instruction count. But actually the CPI is increased, but because the instruction count is reduced more, so the overall performance is improved. Okay. So compiler also can change the number of instructions. Then so because the compiler just change the instruction, so it can use the more optimized instructions. So can reduce the number of instructions. But CPI is can be increased. Okay. So that's why when we just check the performance, then we need to check the instruction count and CPI. Which is the clock cycle is the inverse of the performance. Okay. This is the impact of compiler. Okay. And then also this graph shows the different aspects at the different programming languages and algorithms. So this is the performance of bubble sort. Bubble sort is the very basic sorting algorithm, right? It's a very basic sorting algorithm, right? And C means we use the program C as the C for writing a bubble sort algorithm, and then we can find the Java and Java JIT, so just-in-time compiler. So, and then this is the relative performance. Okay. So what can you observe? So it's a C, but it's a no optimization. It's a 1. It's a baseline. So if we and then we use optimization option, then the performance is increased. But if we use Java, performance is increased dramatically. Okay. So Java is also the compiler language like C, but the Java use the Java virtual machine. Okay. So the Java generates the binary file. This binary file is the same, but the Java virtual machine translate this Java binary file, Java binary code into some specific instructions, such as the x86 or ARM. So Java virtual machine translate the Java binary code into the machine instructions in runtime. So that's why if we use the Java virtual machine like this option, the performance is so low. Okay. But if we use a Java just-in-time compiler, then performance is similar to C, but it's slightly lower than the C. Okay. So what does that mean? The performance of an application also is influenced by programming languages. Obviously, right? How about the Python? Python is extremely slow, right? So as I mentioned, the Python is actually the mechanism is different. The Python is the interpreter language, not compiler language. So Python is actually extremely slow. Okay? So the performance of an application is also influenced by programming languages. So another this is the quick sort result. Okay. And then, so quick sort is the enhanced sorting algorithm. Okay. So, and then also you can find that if we use the all three options in GCC, then actually performance is dramatically increased. Okay. So, because the algorithm is changing. Okay. So if we just change algorithm, the optimization, compile optimizations can affect the different degree. So it means that some algorithms are highly influenced by compiler optimization. So this is the example. If we use the O1 or O2, then the performance is increased by 50%. But if we use the O3, it is around the above. Okay. And then the last graph shows the performance by peak sort compared to bubble sort. And then the y-axis is the speed up. So I mentioned that the quick sort is the enhanced sorting algorithm. Okay, it means a fast. It is a fast. How much? Around the 1,000 times. Okay, and so if no optimization is applied, the quick sort is faster than bubble sort around the 2,500 times, right? Like this. So it shows that actually the algorithms are also very critical. Okay? Compile optimizations can change the performance of our program, our computer system, but algorithms are actually also very critical. Okay? So what can we learn? So compiler optimization. So sometimes, so if we just apply compiler optimizations, then we can improve the performance. But compiler optimizations are sensitive to algorithms. Okay? Nothing can fix or down algorithm. So what does that mean? We use good algorithm to make a code. Okay. So like this. So that's why algorithms are critical. Algorithms are very important. Okay. We need to use the optimized algorithm. Algorithm also critical for the parallel processing such as GPU. Okay. So it is because nothing can fix a down algorithm. Okay. So it's very important. But we learned that compilers can also change the performance of our applications. Okay? So it is because, as you know, so we can actually in the first class, so we learned that the computer system is composed of many layers, and then these layers are actually all these layers are important for the performance of a computer system, like architecture, hardware, and then operating system, compiler, and application. This is algorithm. Okay. So because the computer system composed of many layers, and actually we need to optimize these layers, okay, in order to increase the performance of our computer system. Okay. So we learned about the compilation process. Okay. Then let's learn about the detailed instructions. Okay. So until this point, we learned how the high-level language code is translated into machine code. Okay. So sometimes you can think that, oh, this is not easy to understand, because as I mentioned, we do not learn about some concepts like the virtual memory, the arguments, some function calls. Yeah. So you may think that, oh, this is not easy to understand, but it's okay. Okay, I guess it's okay. Okay, we will learn. But I just want to introduce some high-level process, like how the instructions are generated, how the instructions are allocated in the memory, and then how the computer systems, how CPUs read instructions in the memory. So that's why I first introduced about some compilation process. Okay, try to understand. This is some overview. There's an overview of the like the application and how the applications are executed in a computer system. Okay, now let's learn about the instructions. So instructions are defined in instruction set architecture. So it means the computer architect defines instructions. So think about the RISC-V. So RISC-V is a rather brand new instruction set architecture. So as I mentioned, the x86 has very long history. That is the same to the ARM. So ARM has also very long history. But RISC-V, so RISC-V was recently designed. I said designed. That means some researchers designed RISC-V instructions, right? So there can be some rules, so some principles for ISA design. So these are principles for ISA design. Okay? Like simplicity favors regularity, and then make the common case best. So actually, this is very important. Smaller is faster, and good design demands good compromises. Okay? And these are some principles, okay, for designing instructions. So let's see how the instructions are designed and how instructions are organized in RISC-V. Okay, let's start with the arithmetic operations. So what are arithmetic operations? So like addition, subtraction, multiplication, or division, and these are arithmetic operations. Then how can we handle the arithmetic operations in real life? So like the 1 plus 2 equal 3, right? So plus is the an operator. So it's an operator. An operator defines the type of arithmetic operations. So we can use the plus, this is the addition, and then minus, this is subtraction, multiplication, and division. These are operators. And then what is this? 1 and 2. 1 and 2 are operands. Okay, operands. Then 3 is the result, right? So actually, in order to represent arithmetic operations in real life, we require operator and operands and result, right? This is the same to instructions, right? So it is because in CPU, so actually the CPU processes number data, right? CPU processes digital data, but actually the CPUs process digital numbers. Okay, numbers, right? So the arithmetic operations are actually the basic operations, the basic instructions in CPU, basic instructions in the ISAR, the instruction set architecture. So this is the example, like add A comma B comma C. Okay, and then it is defined as the A equal B plus C. So this is the form of an instruction. The instruction has the instruction part. So this is similar to the operator of the arithmetic operation. And A is the destination, like the result part, like this one. Okay. How about the B and C? B and C, you can find the B plus C equal A. So B and C are operands. So it's the same. Like the real world arithmetic operations, so we can just represent these operations using instructions. That's how instructions are designed for computer system. Okay. And then in the RISC-V or other RISC type ISA, all arithmetic operations have this form. So if you see the ARM instructions, ARM instruction is very similar. ARM instruction also has this form of add instruction. It's the same to MIPS or ARM or RISC-V. x86 is similar, but x86 is more complex. Okay, so here we can find the design principle. One, simplicity favors regularity. So you can find that all arithmetic operations have this form. Okay, like we can just change the add to the sub. It means the subtraction, and then mod, and then divide. So we can use some other logical instructions such as the and then or, this exclusive or. So you can find arithmetic and logic instruction have the same format, like add destination and two operands, like add ABC, or sub ABC, multiply ABC. So regular instructions have regular, exhibit the regularity. And then so we can define simpler instructions. So you may think that, oh, we can define some different instructions such as, like, it is possible 1 plus 2 plus 3 equals 6. Okay, so then we can say add some new instruction like add 3, A comma B comma C comma D. So it uses the 3 operands. It can be possible, but regularity is actually this instruction does not this instruction breaks regularity. So actually if RISC-V has this form of arithmetic or logical instructions. And then A comma B comma C, 2 operands and 1 destination. Okay. It can be possible, but it's not supported because of this principle. Simplicity favors regularity. So I think we can easily understand. So this is the C. So actually so I will show the example C code and then some compiled RISC-V assembly code. Okay. So this is the C code A equal B plus C. So this C code is translated into RISC-V assembly code. So because so in the C code, you can find the add operation, operator. So we use add instruction. Then, this is the destination. So A is the destination operand. And B and C. B and C are source operand. Okay. So this add instruction is translated into RISC-V like this. Okay. Then solve is the same. So I said that all arithmetic instructions have the same form, like add A, B, C, what? Solve A, B, C. So C code A equal B minus C is a solve ABC, right? Okay, simplistic table regularity. There are two sources, one destination. Okay, and so instructions use the same number of operands. How about this one? So in a C code, so this is more complex operation, like A equal B plus C minus D. Okay, so but in the RISC-V, this C statement is translated into two instructions like this. So it is because, so in this, as I mentioned, in this statement, we can find three source operands, E, C, D. But RISC-V does not support arithmetic operations that handle three source operands. Arithmetic instructions have only two source operands. Okay, so enough to this C code is translated into two RISC-V instructions. Okay, you can find that firstly we compute P plus C, and then it is put in the temporary register, the temporary destination at T, and we perform the T minus D. Okay, and we get A. Okay, so this is the some example of some multiple instruction generation of multiple instructions. Okay, so also the another design principle is the common case fast. So it means that actually the hardware is designed for the fast operation, right? So everyone wants to buy high performance. It means the fast hardware. So actually, in order to build a fast hardware, so it means in order to build a fast computer system, so actually, so we know that in a computer system, CPU execute instructions. So it means, so in order to make a fast computer, then it means CPU needs to process instructions quickly. Okay, and how make common case fast. Okay, so the instruction, so it means that actually, so for this instruction, we can define some new instruction like add sub, the more complex instruction. But the RISC-V just use the very simple instruction, and then these simple instructions are processed quickly. This is the common case fast. Okay. So more complex instructions can be implemented using multiple simple instructions. Okay, this is the design principle. So that's why the RISC-V instructions define very simple instructions. Is it because the CPU can execute simple instructions fast. But if the instructions are complex, then it will take longer time. Okay, so instead of using complex instructions, the RISC type instruction just define very simple instructions. Then the simple instructions are processed quickly in the CPU. This means the make the common case fast. So this is very important design approach. Okay. Okay, so I think you can start here. And then so you can find the CISC here. The CISC is the important concept. Okay. Okay, I'll stop here. Any questions? So thank you for your attention, and then see you in the next class. And now